Today we can begin with the azeotropes. Azeotropes are constant boiling liquids. That means it is a mixture of two liquids which distills out without any change in composition. That means it is not possible to separate them by distillation. For example, ethanol water mixture, 95% ethanol in water. If you boil it, the mixture will boil at a particular temperature and will evaporate. When you collect it in another vessel, that also will be 95%. That is an azeotrope. Azeotropes, which are binary mixtures having the same composition in liquid and vapor phase. When you boil it, what happens? It will distill out without any change in composition. So what is an azeotrope? Azeotrope is a binary mixture which is distilling out without any change in composition. Or we can say constant boiling liquid. There are two types of azeotropes. Minimum boiling azeotropes. We already discussed that there are non-ideal solutions with the positive deviation and negative deviation. In the case of positive deviation, you know there is a positive curve. So what is boiling point? Boiling point is the temperature. Boiling point is the temperature at which vapor pressure of the liquid becomes equal to atmospheric pressure. So vapor pressure curve that is positive. So when we consider azeotropes with the positive deviation from ideal behavior, we can see the gap between the vapor pressure and atmospheric pressure, that is very small gap between vapor pressure and atmospheric pressure. So at a lower temperature, what happens? The boiling will take place. Since the gap is very small, at a lower temperature, the boiling will take place. Therefore, they are known as minimum boiling azeotropes. So what is minimum boiling azeotropes? The solutions which show a large positive deviation from Raoult's law form minimum boiling azeotrope at a specific composition, not in all the composition, only at a specific composition. Example, 95% ethanol water mixture. Then what is high boiling or maximum boiling azeotropes? The solutions that show large negative deviation from Raoult's law, they form maximum boiling azeotropes at a specific composition. That is possible only at a specific composition. Large negative deviation. Nitric acid water mixture is an example. Nitric acid water mixture is showing negative deviation, not in all the compositions, but only at a particular composition. These are azeotropes. Now, colligative properties. And before that, we have to discuss we have to compare Raoult's law and Henry's law. What is Raoult's law? P1 is equal to P1 0 into X1. What is Henry's law? P is equal to KH into X. When you compare these two, you can see P1 0 and KH. That is the only difference. In the case of gases dissolved in liquid, P is equal to KH into X. KH is a constant. But in the case of two liquid mixtures, the partial vapor pressure P1 is equal to P10 into XA, where P10 is vapor pressure of pure component. That's also a constant. So when you compare Raoult's law and Henry's law, we can identify Raoult's law as a special case of Henry's law. In Henry's law, gas dissolved in liquid. Instead of a gas, what happens when a volatile liquid dissolves in liquid? Then partial pressure replaced by partial vapor pressure. That is the only difference. Partial vapor pressure P1 is equal to P10 into X1. If you write these two equations very close to each other, you will understand it properly. Okay, now colligative properties and determination of molar mass. Colligative properties are the properties which depends only on the number of particles present in the solution. They are known as colligative properties. That is not depending on the nature. Independent of the nature of the solute and solvent, but depend only on the number of particles present in the solution. Here we have to discuss four important colligative properties. The first one, relative lowering of vapor pressure. Second one, depression of freezing point. Third, elevation of boiling point. And fourth one, osmotic pressure. Which are the four colligative properties? Relative lowering of vapor pressure, depression of freezing point, elevation of boiling point, and osmotic pressure. And we have to see it in detail. What is meant by relative lowering of vapor pressure? Or what is depression of freezing point? What is elevation of boiling point? And what is osmotic pressure? We know when we prepare a solution, what happens in the surface? Some of the solvent molecules are replaced by solute molecules. And if these solute molecules are non-volatile, then what happens? The evaporation will decrease. Due to the decrease in evaporation, the vapor pressure also decreases. So we can say vapor pressure of the solution will be always less than the vapor pressure of the pure solvent. Because the evaporation of solvent molecules are prevented by the presence of non-volatile solute molecules. Therefore, vapor pressure of solution will be always less than vapor pressure of pure solvent. Based on this, the first one, relative lowering of vapor pressure, we can study the relative lowering of vapor pressure. When a non-volatile solute is dissolved in a volatile solvent, that is a condition. Non-volatile solute is dissolved in a volatile solvent. The ideal vapor pressure of, the total vapor pressure of the solution, that is PS, total vapor pressure of solution PS, that is equal to P1 plus P2. But P2 is non-volatile, so it has no vapor pressure. P2 is 0. Therefore, PS is equal to P1. PS is equal to P10 into X1, Raoult's law. But we know X1 plus X2 is equal to 1, or X1 is equal to 1 minus X2. Instead of X1, you write 1 minus X2. Then PS is equal to P10 into 1 minus X2. Or PS is equal to P10 minus P10 into X2. P10 into X2 is equal to P10 minus PS. Or X2 is equal to P10 minus P1 by P10. Here P10 minus P1 by P10 is known as relative lowering of vapor pressure, and that is equal to X2. Relative lowering of vapor pressure is equal to mole fraction of solute. Relative lowering of vapor pressure is equal to mole fraction of solute. So we can consider it as another statement of Raoult's law. In a binary solution containing non-volatile solute and volatile solvent, relative lowering of vapor pressure is equal to mole fraction of solute. That is another statement of Raoult's law. You can write it as second statement of Raoult's law. What is second statement of Raoult's law? You tell and write it. What is second statement of Raoult's law? In a binary solution of a non-volatile solute in a volatile solvent, relative lowering of vapor pressure is equal to mole fraction of solute, or P10 minus P1 by P10 is equal to X2. Here, P10 is the vapor pressure of the pure component, minus P1. What is P1? You can see PS is equal to P1, vapor pressure of the solution. P10 minus P1 divided by P10 is equal to X2. Or vapor pressure of pure component minus vapor pressure of solution divided by vapor pressure of pure component is equal to mole fraction of solute. And in the case of colligative property measurement, one of the important applications is to determine molecular mass of unknown solute. Or to identify the unknown solute. What is the molecular mass of unknown solute? So what is the important application of colligative property determination? To find out or to calculate molecular mass of unknown solute. Molecular mass of unknown solute, that is application. So we have to rearrange second law of Raoult's law, the statement of second law of Raoult's law, in order to calculate molecular mass of unknown solute. P10 minus P1 by P10 is equal to X2. What is X2? N2 by N1 plus N2. N1 number of moles of solvent, N2 number of moles of solute. So N2 divided by N1 plus N2. What is N2? W2 by M2. N1, W1 by M1. But we know colligative properties are the properties of dilute solutions, very dilute solutions. So always number of moles of solute will be negligible as compared to number of moles of solvent. So N1 plus N2 approximately equal to N1. So we can rewrite this equation as P10 minus P1 by P10 is equal to N2 by N1, or P10 minus P1 by P10 is equal to W2 by M2, that is N2, divided by W1 by M1. That we can write as W2 divided by M2 into M1 by W1. So here, what you have to find out? M2, molecular mass of solute. So this equation can be used to find out molecular mass of solute. Here W1 and W2 are the masses of solvent and solute. M1 and M2 are the molar masses of solvent and solute. Two problems, you can see two problems here. The vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid weighing 0.5 gram when added to 39 gram of benzene, molar mass 78 gram per mole. Vapor pressure of the solution is then 0.845 bar. What is the molar mass of the solid substance? Here vapor pressure of solution is given. What is vapor pressure of solution? 0.845 bar. Vapor pressure of pure component benzene is given 0.850. So we can find out relative lowering of vapor pressure. 0.850 minus 0.845 divided by 0.850. Now that is equal to W2 by M2. W2 is given 0.5 gram. M2 is unknown. Into M1 78 divided by W1 39. So we can solve it here. So a simple substitute. It is the equation P10 minus P1 by P10 is equal to W2 by M2 into M1 by W1. So 0.850 minus 0.845 divided by 0.850 is equal to 0.5 into 78 divided by M2 into 39. So what is M2? M2 is 170 gram per mole. Is it clear? Okay, you take a paper and solve it, then you will understand. Now the second question. The second question, calculate the mass of a non-volatile solute, molar mass 40 gram per mole, which should be dissolved in 114 gram of octane to reduce its vapor pressure to 80%. That means 20% decrease is required. So by adding a very small quantity of solute, it is not possible to attain. Large quantity of solute is needed. If you are adding large quantity of solute, then it is not a dilute solution. If it is not a dilute solution, can you assume N1 plus N2 is equal to N1, approximately is equal to N1? No. So such a approximation is not possible. That is the importance of this question. Calculate the mass of non-volatile solute, molar mass 40 gram per mole, which should be dissolved in 140 gram octane to reduce its vapor pressure to 80%. So here, this is a different question. That is why I'm giving it to you. Here, what you have to listen, for a 20% decrease in the vapor pressure, you need comparatively higher quantity of solute. Therefore, N1 plus N2 nearly equal to N1, that approximation is not possible in this problem. That is the only thing you have to listen. You can see the solution here. So here, what is the equation? P10 minus P1 by P10 is equal to N2 by N1 plus N2, not N2 by N1. That is the difference. So complete equation is required. P10 100, you can take it as 100, P1 80, percentage is given. So 100 minus 80 by 100. That is equal to, what is N2? W2 by M2 divided by what is N1? W2 by M2 plus W1 by M1. Now substitute the values. 100 minus 80, 20. 20 by 100 is equal to W2 by 40 divided by W2 by 40 plus 114 divided by 140. 1 by 5 into W2 by 40 plus 1. 114 divided by 140 equal to 1. That is equal to W2 by 40. Or W2 by 40 plus 1 is equal to W2 by 40 into 5. W2 into 5 by 40. Then you can calculate W and you can see it is equal to 10 gram. And there is a reduced form of equation for this. In such case, if the solution concentration of the solution is comparatively more, then there is another equation. Those who are interested, please note it. The equation is P10 minus P1 divided by P1. That is vapor pressure, total vapor pressure of solution is equal to N2 by N1. What is the equation? P10 minus P1 divided by P10 is equal to N2 by N1. Instead of P10, what you have to write? P1 or vapor pressure of solution. Then you will get the same answer, 10 gram. Okay, very small portion. So I will give you these two problems as assignment and one more question as the assignment. All of you have to answer the questions and send in time. Okay, today we can stop here.